Hello, Debbie. This is Johnson City. Can you hear us and see us okay?
I can. Can you see us?
I can see you and hear you fine. Do me a favor. Is his computer on and ready to go?
It should.
Would you share the content, please? Because I was using the projector down here for something earlier. I hit stop graphics, but I think you all need to share. Just hit the podium PC on the Crestron for me.
Okay.
Debbie, hang on a minute.
Did that do it?
Yep, there it came in. Thank you. I just didn't want you to get too far until it took a little longer than it normally does, but we have your computer down here now. Great. Thank you.
Okay, thank you.
The first thing tonight is you have homework 5 for me. Make sure you get your name on those, please.
Can I email mine to you? Okay.
Hey, just think with that.
Where's this?
The next thing is that we're going to have test 2 on Tuesday, April 2nd. It's going to cover chapters 6, 8, 9, 12, 13, 15, and I think 16. It'll look the same as the other test. It's got 40 questions, multiple choice, A, B, C, and D. The only thing that's changing is the material. You need to make sure you bring some version of an ID, calculator, and your formulas and tables that you've used for the first test. Rob, you there?
Hey, Mike.
Hey, Tuesdays is good for you, right?
It's perfect.
For the other room.
Yeah, it's clear. It's open right now if we needed it.
Yeah, I got you. That's the reason I was trying to do it Tuesday. So I'll be sending an email to you streamers when I get back upstairs, but if you're going to, I'm assuming like the first time you're going to use the same thing. This time, if you're going to Johnson City, you'll be going to Brown Hall 133. If you're coming to Kingsport, we're in room 232. But I'll be sending an email, like I said, when I get back upstairs to see if your plans have changed for test 2 from test 1. I mean, if you're using a proctor, that's fine too. If you're coming to see us here, or whether you're going to Johnson City, I just wanted you to know where you're going here. The other thing is this, is that the capstone project, remember we did the class survey, they collected data. I've got all the files and everything needed and ready for you in D2L. They will show up at 7 o'clock tonight. Now, the capstone project, when it is due on Friday, the 26th of April. That's the last day of the semester. Hell, that day me and you don't even meet. We meet the Thursday before that, and it's due at 5 p.m. So here's the way this works. What I've done is this. I have posted everything that you need in D2L. This is under content, and it's under the capstone project part, right? So what is it, like 6 or 7 down? You'll notice there's a spring 2019 instructions. That's just mean you're going to look at that anyway. There's the actual capstone project, which is a Word document, which is where you're going to do all your work. And then there's actually the capstone mini-tab data file, the spring 2019 capstone data. That's where you get your data from. My suggestion to you is when you download that capstone data file, that you put it on your home computer wherever you got all those rest of those files you've been using mini-tab through Gold Lab with. That way you know exactly how to find it. The other thing is this. If some of you have a problem with downloading that capstone data file, send me an email and I will send it to you as a zip file, and then I know everybody's computer. You can take the zip and you can open it and pull that file to wherever you need to have it. The other thing that's here is I have posted the solutions for the one from last fall, last spring, the fall before that. I've posted the solutions for the last 4 that we've given, right? The reason for that is so that you have something to look at to see what you should be writing. Are the problems exactly the same? Obviously not, because the questions on the survey have changed. Are they very similar? Yes. On one of those 4, you will find something that's very, very similar to what you are doing for yours. All right? Now, what I have done is this. I have downloaded those files to my Q drive so that I can always bring them up, because I'm going to bring them up about every night here at the beginning of class for maybe 10 minutes or something so we can talk about it. I would like to look at the instructions first. And so the instructions are, I'll show you about typing your name, your E number, your section number in the Word document. It says do your own work. It's academic misconduct to copy or seek assistance from other people or to share your work with other students. Any academic misconduct from this project will result in a grade of 0 and a written report of symptom things. And I will get my ruler out and slap you on the back of the wrist. Here's the thing. I know some of you folks work with each other on the homework. I can see that happening here, but you got to do your own work. It's not like I can put them together and see them perfect, right? I mean, you can talk about it. But, you need to do your own work. It's worth 10% of your grade. It's 100 points. It's due via the Dropbox and D2L titled Capstone Project. That's what I told you before. I will not take anything after Friday, April 26th at 5 p.m. All right? While we're here, I'm here. Dropbox. There's one that says Capstone Project. It'll start at 7 o'clock tonight. That's where you're going to upload that whole Word document to. All right? What else we got here? Please start each problem at the top of a new page. Look, you're just making my life a little easier because that's the way it's given to you. Like, okay, we start a new problem, we start a full page. You just make it a little easier for me to grade. You read that note. Insert all the graphs and Minitab output within a problem as requested. In other words, if it says put the graph here, copy and paste it there. Do not attach all your shit at the end. I will not look at it. Okay? If you're using a Mac, but your instructor's not, which would be me part of the time, save your document in these MS Word format .doc, PDF or rich text. If you're a Mac person and you got the ability, you need to save it as a PDF. I cannot read it in pages, which is the word processing that's only on the Mac, right? So if you don't have the, where you can save it to me as a Word document and upload it, do a PDF, that'd be fine, until I can read that, all right? The rest of the instructions are, here's the questions they must have asked you. If I remember right, there was like 15 of them. And then there were 635 students that answered. All the data's in that spring 2019 capstone data file. And then that's how the Minitab file is laid out for you. Does that really mean anything to us? Not really. All right? It's up here. You got to be done at a certain time. Do your own work. You're going to upload it. All right? We're done with that. You'll never see me pull that up again. Now, here's what the capstone project looks like. There is, I think there's 7 questions. There's been 7 questions for quite a while now. Yeah. The reason I scrolled through it like that, if you think you're going to do this on April 25th and get it to you by 5 o'clock on April 26th, that ain't going to happen. First off, who knows if frickin' Minitab through the Gold Lab is going to work perfectly for you all the time. So you kind of want to do this as I'm talking about things. I would like for you to be doing things too. If I'm going to spend like 10 minutes in class talking about this, I would appreciate it, that you're kind of following along. Now, the other warning is this, is you won't be able to do it finish early. Because the last night of class, we'll be talking about the very last thing we need to talk about here. Sorry, that's just the way the class is going. It's the way it works out with me every semester. All right? Now, if you'll come here and you'll double-click this header, see, I can put my name in there. Section number, so on and so forth, right? I can come down here, you see how I'm doing that. All I did was double-click in the header there, and then up here it says close the header, and then my name stays and all that. It's all right. When you upload that file, how about putting your name in the title there, too? That would kind of help me a little bit. And then you'll notice, not number 1, but number 2, it says something about speed. You must ask how fast you've driven an automobile on the highway. It says create an appropriate graph to display the distribution and insert it here. That's what I mean. You copy and paste, you put everything where it belongs. Right? If it belongs there, you put it there. Now, what I would like to do tonight for the first 5 minutes is I'd like to take a look at number 1. I've already got Minitab open here. Now, I haven't uploaded the Minitab file, but I'm going to for us. Like I said, I put everything on my Q drive because it makes it easier for me to work here with you guys. And the data files for spring 2019, remember, you're going to save them wherever you save the rest of those files. And what I'm talking about are the ones you downloaded out of Sapling Learning. And you'll notice, we've got all these columns. The instructions told me what the columns were. The first one's just an ID, then their age, and their gender, their race, and so forth. And then we're all, I don't even scroll down, there's 635 lines here. How do I know that? There's 635 students. Okay? So that's our file. Now, if I come back over here to the project, and I look at number 1, sampling and the survey data, the variable age. It says, starting with the first observation, number 1, select every 20th until you have 10 observations. Assume the first observation was randomly chosen as the starting point. In other words, the person that made this up, they must have had the numbers like 1 through 10 in a little jar, and they happened to pick 1 this semester. And so they're not going to take the first one. We're going to count 20 from the first one. We're going to take the 20th one, the 40th one, the 60th one, 80, 100. In other words, what we're going to do is, you're going to look and say, oh, well, I need the 20th one. The 20th one's age is 32. The 40th one's age is 25. The 60th one's age is 22. And what you're going to do is, you're going to put them right here, right? The first one was whatever I said it was, right? 32, then 25, and then 22. You're just going to fill in the little blanks there. Everybody follow? So I'm just reading the data file. I'm going to pick the 20th one, the 30th, 40th one, 60, 80, 100, 120, 140, until I get 10. Right? Until I fill up that little boxes there. Yes? And then it says the mean age of the 10, above 10 students is, how are you going to do that? You're going to pull your calculator out, and you're going to calculate, you're going to plug in those 10 numbers and divide by 10 and tell me what the average age is. Everybody okay with that thought? I don't have any tricks here, right? You're going to take the 20th, 40, 60, 80, 100, 120, 140, 160, 180, 200. That's going to be your 10. Whatever those ages are off that data file, you're going to add them up, divide by 10, and give me the average. What type of sampling was used in Part A? Anybody know? Does anybody know when I randomly choose a starting point and I pick every 12th one, or 8th one, or 10th one, or in this case, every 20th one is? I'm thinking that's like that systematic random sampling. I'm thinking. Now, you know if I'm thinking it, it could be right. Look, and I apologize up front for anybody that doesn't want to hear me talk about every problem on the project. If you don't want to hear me talk about every problem on the project, when you come to class, just cover your ears. If you're sitting at home, just turn the audio off, right? Because I'm going to do this. It says next, select a simple random sample of size 10. Get Minitab to do it. All right? Here's what you're going to do. You're going to come here, and you're going to count random data. The instructions are on the project, though. They're telling you exactly where to go. And you want to sample from columns. How many do I want to sample? What did it say? I wanted 10. Right? I want a sample of size 10 here. From what columns? I actually want 2 things. I want the person's ID, and I want their age. So I'm going to double-click their ID, and I'm going to double-click the age. All right? The instructions are there. They tell you exactly what to do on the project. And then I need to store this random sample of size 10 somewhere. And so just to be safe, I'm going to give it 2 columns that I know are blank out the end. I'm going to choose column 21, and I'm going to choose column 22. I knew I was only like a 16 or 17, so I'm far enough out. And I'm going to click OK. Everybody okay so far? Now, obviously, it doesn't look like it did anything, but you'll notice it tells you exactly what to do. Go to calc, random data, sample from columns, type the number 10 in, exactly what I did. They gave you the instructions there. If you come over here and look, and we go across to columns 21 and 22. I'm going to slide that window up a little bit. So the first person that my random sample has an ID of 275 and an age of 19. The second person has an ID of 145 and an age of 20. The third person's got an ID of 381 and 18. And so when I come over here, I'm going to put their, notice in this little table here, I'm going to put their ID and I'm going to put their age. Do you understand that when you do this, you're going to get a different answer than I just got? Do you understand everybody everywhere that I have is going to get a different answer from everybody else? Yes? The way I can show you that is, let's go right back and do it again. Calc, random data, sample from columns, everything's already fixed. If I click OK, what's column 21 and 22? Obviously, I get a different random sample of size 10. Look, what Minitab is actually choosing is, it's choosing a simple random sample of size 10. Okay? So we're all going to be different at that point. I'll give you, in Part A, we're all going to be the same, have the same meaning. Here, we're all going to have a different sample, different IDs, different age, different meaning. What was the type of sampling used in Part B? Part D? What was Minitab choosing? It chooses our SRS, right, our simple random sample. It says, suppose we think of all students who responded to the survey, all 635 of them, as the population for the purpose of this problem. In that case, the population mean average is 19.839. They're giving me that. In other words, they took the average of all the ages of all 635 students that responded and got a mean of 19.839. Discuss two or more complete sentences, the differences and similarities between 19.839 and the answers you got in B and E. Well, I'm going to give you, obviously, your systematic random sample and your simple random sample gave you a different answer than what you're seeing for the population. Everybody understand that, right? You're not going to be exact. For all I know, one of them overestimates what the truth is and one of them underestimates what the truth is, right? I don't know. I can't really answer here until you do your work and see what you did. Tell me what you think. What I do know is this. If we did this over and over again, as you're going to see tonight, those sample means all right, I know two things. I know after tonight that if I kept track of all these simple random samples, I did this like 100 times, they'll be close in on what that 19.839 is, right? Sometimes you'll overestimate, sometimes you'll underestimate. But eventually you'll form a nice pattern. See how my hands are moving? My hands are moving a nice pattern and they'll all be clumped in on that mean, all right? We just took care of problem number 1. We only got 6 to go. Please be careful. There's a 2E and there's a 2O. 2E is for the people where the E number ends in an even number, 0 through 8, and 2EO is for the ones that end in an odd number. Right? So you know your E number, you're going to put it in the header there. So whichever problem you don't do, could you do me a favor? Would you wipe that out of your project? Right? If you're going to do 2E, don't leave 2O there. I would appreciate that. It would help me a little bit. And there's somewhere else they do that to us. Maybe it's number 5. 5, T. If the sum of the digits in your E number are even, do this problem. 5H, if the sum of the numbers in your E number are odd, do this one. Right? So you only do one number 5, and you only do one number 2. Yep. Are we okay with the first problem? And then on Thursday, we'll have a little talk about number 2, and so on and so forth. Look, what I think is this, is you can do number 1, you can do number 2, you can do number 3, 4, half of 5, T or H, and that's as far as you can go now. That's all the material we got through, right? We have to do some more, cover some more material to do the bonus that's on 5, 6, and 7. We haven't gotten there yet, all right? So that's where we're at. Everybody understand what's going to happen? If you have a problem downloading anything, send me an email. I will send it to you so that I know that you can download it. Now, where me and you left off on Thursday is we were in chapter 15. I want to remind you the title. Chapter 15, Sampling Distribution. Okay? Now, here's the other thing is, you saw what I did to you with the project there? Like I didn't give you time to write down. It's not because I don't want to give you time to write down, but you got to understand, I got to work that in with the material that's left, and we are being recorded. And you know it's always going to show up at the beginning of the recording, right? For the first 10 or 15 minutes of class. So you can always go back and look and see exactly what he did. Most of the time I'll give you some thought about how to answer the questions, but it's more about using the mini tab and getting the right things. All right? Now, Chapter 15, Sampling Distribution. I want to remind you the thing we talked about last Thursday. The law of large numbers. I'm going to point you to the page number again. That's on page 354. I'm not going to write anything down. I'm going to read it to you, and it says, draw observations at random from any population with a finite mean mu. In other words, you've got this population that's got some mean mu that we're thinking about as this parameter. As the number of observations drawn increases, what we're talking about is we keep adding more and more individuals from the population to our sample. And as we do that, the mean x bar of the observed value, the mean x bar, your statistic from your sample, is going to get closer and closer to mu. So the way I think about it is as n increases your sample size, X bar gets closer and closer to mu. And where I ended up on Thursday was saying, well, look, the best thing we could ever do was just do a census and sample the whole population, then my X bar would be exactly equal to mu. So it kind of makes sense as my sample size increases that my X bar becomes a better and better estimate of mu, right? My statistic becomes a better and better estimate of mu, all right? So, to the main topic here is sampling distributions. Okay? So here's the thing. If I think about this example 15.3 here. Okay? I want to look at it just a second. And it says this. Suppose the distribution of odor thresholds of adults has a mean of 25. So they're telling me something here has a mean of 25. Right? And it's the odor threshold. It's like the odor that people can smell. It has got a mean, so it's like so many parts per million. It says the mean mu is the true value of the parameter. In other words, this is your parameter. When I'm looking at this mean odor threshold of all adults, that is about your population. You can tell it is without me saying it, because I'm using mu for that. All right? Then it says, figure 15.1 on page 355 shows how the sample mean X bar of a SRS drawn from a population changes as we add more subjects. What I want you to look at is this. I'm going to draw this little picture real quick. I've got this little graph, and I'm going to put this little line in here at 25. You notice that's my mu. And down here is your, I've got to write, I know the book's saying number of observations, but folks, this is your sample size. N. And what I want to show you is what happens here. So, as they take one person and measure their odor threshold, and they take another person and take the average of those two, what you're going to see happen with your graph is, the mean of one person, let's say that's 1, and we go to 5, and then 10, and I'm all the way out here at 50, 100, and so forth. So the first person had a mean odor threshold bigger than 25. Okay? And then the second person, let's say theirs was below, so, they came down here somewhere, and then I jump up, maybe I jump there. But what happens is, I start adding more and more people. I should be drawing you little lines like this. I'm looking at the mean of however many are in my sample at this point. And when I get out here, we start getting closer and closer and closer. Now, the reason I wanted to look at this is because that's the law of large numbers. It gets close to 25 and it stays there. In other words, you're looking at your sample size reading from left to right increases, your little mean, your little X bar. That's what we're plotting X bar with the little dots there. I'm connecting the lines just to show it like that. We're getting close to 25. Now, the catch is, in this experiment that they did to do all this, they used N equals 10 subjects. So I've got two things going on here, right? I got the one where I showed you the law of numbers, and then when they actually did the experiment, they had 10 subjects there. All right? So the question is, what can we say about X bar from 10 subjects as an estimate of mu? Now, the reason this question is being asked is because of that right there. The law of large numbers is not going to help you when your sample size is only 10. I can't tell you that I'm going to be close or not. Right? So, I circled that, starred that. I'm going to write no law of large numbers. Not going to help me. If my sample was 100, then I'd be fairly confident to say, oh, I expect X bar to be a good estimate of me. But at 10, that's a small sample size. Okay? What we want to know is this. I apologize for hesitating. What I want to know is this. All right? What would happen? I want to know the behavior. I'm interested in the behavior of X bar in many samples of the same size from the same population. That's what I'm interested in. What does those X bars look like? What do the X bars, what do those different statistics, what do those different sample means look like as I take many, many samples, and every time I take a sample, I calculate an X bar, right? I calculate the mean over threshold for those 10 subjects. What do they look like? Do they settle down to a pattern that we can think about here? All right? So here's what I want to do. Okay? I want to do a couple things here. One is I want to take 1,000 samples of size n equals 10. In other words, I'm going to do this 1,000 different times. 2, I want to calculate X bar for each sample. So what I'm looking at is this. I have 1,000 in other words, I did this 1,000 times where I measured this mean over threshold for 10 individuals at a time and I took their average. So what I really have is I've got 1,000 X bars. All right? 3, I'd like to make a histogram which seems like a reasonable thing for us to do at this point. I'd like to make a histogram of the 1,000 X bars I mean, if you think about it, odor threshold, hell, that's a quantitative variable. Taking the average of that, those X bars, that's a quantitative variable. It makes sense to make a histogram of those. And then if I want to make a histogram, I'm going to underline that twice. What do we always want to talk about? I'd like to talk about, it's been a while since me and you have done this, but I would like to talk about shape, center, spread, outlier. Not so much outlier. I'm really interested in shape, center, and spread. That's what me and you always talk about when we look at a histogram. What's the shape? Is it roughly symmetric, skewed right, skewed left, some irregular shape? Where's the center? Where's that halfway point? What do we talk about the spread, the variability? I'm talking about this. And then we might want to mention something about outliers. So here's what happened. All right? I'm almost to the punchline here. I got to take a look at this example 15.4. Because there's some information I need there. It says, extensive studies have found that the DMS odor threshold, DMS is dimethyl sulfate that people can smell, of adults follow roughly a normal distribution. So we're looking at the population of all adults. All right? It turns out it follows a normal distribution. We know what that looks like, symmetric, single peaked, and bell shaped, all those ones we worked with in chapter 3, with a mean of 25 and a standard deviation of 7. What should I be writing here instead of all the words? Normal, the mean is 25, the standard deviation is 7. Remember, I always give you mu and sigma to describe this normal distribution. That's where we're looking at all adults and looking at this odor threshold for DMS odors. Everybody following here? Normally, I don't know this kind of information. Normally, I don't know about the population like this. I don't know its mean. I don't know its standard deviation. And I sure the hell don't know it follows a normal distribution. But they're telling me this through extensive studies. They know this. All right? Now, it says figure 15.2, which is on page 357, illustrates the process of choosing many samples and finding the sample mean threshold X bar for each one, like 1,000 of them. So, just so we all can see, maybe. Debbie, is that right? No, I didn't. That's right. Maybe.
Put on document here.
Yeah, what did I do wrong? I gotta turn something on, move something. Huh? Oh no, it's switching.
What you got on it?
My book.
Got it and it's not showing up, is it?
I won't play it. It worked the other day. Here's my thought. Here's what I've got, all right? I've got all these people, right? I got my population here, okay? And we're going to take 1,000 samples of size n equals 10 from that population. And then what do I have happen? You know, I'm choosing an SRS. Think about it like this. When I say random samples, I mean SRS at this point with me and you. And the first X bar I get is 26.82. I'm copying the little picture out of the book. The next one I get is 24.28. The next one I get is 25.22. Right? And they're all size 10. And so, you know, I did this for this 10, this 10, this 10. I did it for 1,000 times here. And so I get all these different X bars, and I did it 1,000 times. And what happens is, when I make my histogram, the histogram is going to look like the following, right? I'm going to draw you the histogram here. My histogram is going to look like this. And what you'll notice is, what's that a histogram? One more time. That's a histogram of 1,000 X bars. All of size 10. All samples of size 10 where I calculate the average over those 10. Now, there's no coincidence that that histogram looks like that. And that it's centered where it is. See, I could come back and I could draw. Anybody know what that red curve is? What's the area under a density curve? Oh, I know. My ass is all the way back to chapter 3. That was the same kind of stuff I was drawing for you in chapter 3, right? Same. Okay? That's what happened. Now, I need two definitions here. Because at this point, you know how there's two groups of people? There's the population and their sample. There's the parameter up here. There's the statistic down here. There's a distribution up here. There's a distribution down here. You've got to get, I know, you're going to confuse my ass. No, there's going to be two of everything from now till the end of the semester. I get to one chapter and hell, there's like 4 of everything. All right? So here's my thought. I need two definitions, and I'm going to point you to these. Page 357. There's something called the population distribution. Okay? And I'm going to add the rest of this to it. It's the population distribution of a variable. I feel these two definitions are so important, I'm actually going to write them down. Normally I don't write your definitions, but I'm going to write it down now. The population distribution of a variable is the distribution, okay, of values of the variable among all individuals in the population. Now, if you want to know the truth, me and you have been looking at, in chapter 3, they were always population distributions, right? We were always thinking about, okay, here's my population, and this is the distribution of values among every individual in the population. They were all population distributions. The population distribution is described by a density curve. All right, so somebody's talking to you about, oh yeah, well I'm looking at the distribution of values of this variable for among all the individuals for every individual in the population. They're talking to you about the population distribution, and it's going to be described by a density curve. As opposed to the other definition is the sampling distribution, which is what is new to us. It's the sampling distribution of it's no longer just a straight up variable like the population distribution, it is of a statistic. You know, what we've calculated from our sample of the statistic is the, again, distribution of values. So it's telling me about what values my statistic is taking. The distribution of values taken by the statistic I'm not done yet. So it's the distribution of values taken by our statistics in all possible samples of the same size from the same population. All right. I'm going to back up here and show you this histogram again now that I got these definitions. So, like I said one more time, the population distribution of a variable, that's the same distributions me and you were looking at in chapter 3. Those are the ones me and you looked at all semester where we were looking at all of some population. What's new to us is this idea of a sampling distribution of a statistic. It's telling me what values that statistic takes when I look at all the samples of the particular size, all from the same population. It's describing the behavior of our statistic as we go from one sample to the next. Now, you see this little guy right here? This right here is your sampling distribution of X bar. How do I know that? Because I'm looking at X bars, right? And I'm looking at all samples of size 10 from the population. This right here is an estimate to that sampling distribution. The sampling distribution is actually described by the density curve. We made the histogram to see what that density curve was going to look like and where it was going to be centered. So, a couple things about this histogram here. What would you tell me about the shape of that histogram? Or hell, what would you tell me about the shape of that density curve I got in red? You would tell me it looks roughly symmetric. And if you was looking at that that curve, you'd almost tell me things look normal here, right? Symmetric, single peaked, and bell shaped. Where is the center? Well, it turns out we need some help from the textbook here. And my help is they calculated the mean of the 1,000 X bars. And I hesitate to say this, but you're looking at the mean of the means. Sorry. There's 1,000 X bars. Hell, we know that's our statistic. We know that's our mean. They took the mean of those 1,000 X bars, and they got it to be 24.95. I'm not making that shit up. They calculated it for us. Notice, it's close to mu being 25, the mean of your population distribution. Everybody follows? There's not a shocker here that histogram and that density curve looks like it's centered at mu equals 25, the mean of the population we were talking about. What about the spread or the variability? In other words, they calculated the standard deviation. Well, if things look normal, remember we used the mean for the center and the standard deviation for the spread and the variability. The standard deviation, and what are we talking about? We're talking about the standard deviation of the 1,000 X bars. It turns out is 2.217. Notice it's smaller than the standard deviation of your population distribution of 7. Okay. Look, I can't emphasize these two definitions enough. That's the one me and you've been dealing with all semester. They would be population distributions, where we're looking at what possible values does a variable take among all the individuals in your population. What's new for me and you is you start taking samples and you calculate some statistic. In our case, you calculate X bar. We want to know, how does X bar vary? What's its behavior as we go from one sample to the next? And what tells me that? That's the sampling distribution of X bar, your statistic. Now, I got to write one more line here. Put this in your notes. This is also described by a density curve. The only reason I drew you the histogram was to get a feel for what all the possible samples of size 10 to X bars would look like, not just 1,000 of them. So a population distribution is described by a density curve, and a sampling distribution of a statistic is described by a density curve. Okay? Now, we, me, you, everybody that's screaming, we're going to have a very particular sampling distribution that we're interested in. We're interested in the sampling distribution of X bar. This is our statistic. Well, it turns out we know it's described by a density curve. It has a mean and it has a standard deviation. Mean and standard deviation. That was the only way me and you ever described the center and spread of a density curve, was by getting the mean and standard deviation. Now, the notation goes like this. For the mean, obviously we're going to use mu, because we always use mu for the mean of a density curve. But I need to subscript it with your statistic. Because eventually with me and you, our statistic changes. It's not always X bar the rest of the semester. And we have to distinguish this mean from the population mean. It turns out this guy here is equal to the mean of your population distribution. For the standard deviation, you know I'm going to use sigma, because I always use sigma for the standard deviation of the density curve. I'm subscripting it with X bar because now it's the standard deviation of the sampling distribution of X bar. And it's equal to the standard deviation of the population distribution divided by square root of n, where we are looking at an SRS of size n. Now, before I start giving you little facts here, what these little formulas are telling me, here's what I've got. Okay? I've got a population distribution. Let's say it's nice and normal. So there's my population distribution. It's normal. It's got a mean mu and a standard deviation sigma. We know it's centered right there. Then all of a sudden, we start taking an SRS of size n. And we're going to calculate X bar over those n. So what I get is, I get your sampling distribution of X bar. And I know it's centered at the exact same spot. That's the reason I'm drawing 1 over the top. Right? And I've given you what the standard deviation is. It turns out the sampling distribution is actually polar. But this move here, going from there to there, that's the idea of taking this simple random sample of size n and taking averages over that sample size. I have a question for you, and I'm expecting somebody to answer it. You see that axis right there when you're looking at the population distribution? What lives there? Do X's live there? Do Z's live there? What the hell lives on the x-axis when you're looking at the population distribution? What always lived on that axis when we were dealing with these before? These are X's, right? They're actually values of the variable on that x-axis, yes? With that thought, what lives on this one? Are they Z's? Are they X's? What are they? Well, what lives on the axis of the sampling distribution is averages, your statistics, different values of your statistics, different sample mean, different averages. That's what lives on the axis, the horizontal axis there. Okay? Now, a couple facts about this sampling distribution. The first one is when somebody tells you the mean of your sampling distribution, the mean of the sampling distribution of X bar, that's how I'm reading that, is equal to the mean of your population distribution of the population where you're choosing your sample from. What they are telling you in fancy statistician language is X bar is an unbiased estimate. Well, we like that shit right there. We like unbiased. And how do I know that's true? I got to come back to my picture for a second. You understand that sometimes when we choose a sample and we calculate our statistic, our X bar, we will be on this side, right? Sometimes when you take a sample, you will be on this side. If you are on this side, you are an underestimate. You understand that? Because we're trying to use X bar to estimate mu, and if you're smaller than mu, you're underestimating what the true value is. Over here, it's a overestimate. Right? So your X bar is actually giving you a value larger than what the truth is about the population. So if you're smaller, you're an underestimate. If you're larger, you're an overestimate. But the deal is, as I go from one sample to the next, I'm going to move all over the place, right? It's not like I'm always overestimating or I'm always underestimating with X bar. I'm unbiased. So sometimes when I choose a sample and calculate it, I overestimate. Sometimes when I choose a sample and calculate it, I underestimate. See, if I was always bigger than the population mean, I would be biased. I would always be overestimating. Or if I was always underestimating every time I took a sample, I would be biased. We like the fact that sometimes you are overestimating and sometimes you are underestimating. So that's the way to say it, knowing that that mean of that sampling distribution is equal to the population mean. That's what we have here. 2, when I look at this little standard deviation, now I write sigma subscripted with X bar. I say the standard deviation of the sampling distribution of X bar. When I tell you it's equal to, what that's telling me is a couple things. Averages, because that's what we're looking at with X bar and the sampling distribution of X bar is averages. Averages are less variable than individual observations. How do I know that's true? You see where you're dividing by the square root of n? As long as n is bigger than 1, the standard deviation of the sampling distribution of X bar will be smaller than the standard deviation of the population distribution. Why? Mean you got to have some number sense here. You understand that sigma is the standard deviation of the population distribution. Sigma is the standard deviation of individual observations, right? That's the population distribution. As long as n is bigger than 1, you're making the standard deviation smaller because you're dividing by the square root of 10 or the square root of 30 or the square root of 50, whatever in the hell your sample size is. Do you remember me telling you the following? Larger sample. Give more accurate results. I can't remember what chapter that was in. Actually, it's chapter 8. There's the formula that tells me that. Right there. As your sample size increases, your standard deviation gets smaller and smaller, and your sampling distribution does this. The sides of it get pushed in, it gets taller, and more of the observation, the X bars are closer and closer to your mean. That's the formula that tells me larger samples give more accurate results because of the variability, the spread, the standard deviation gets smaller as your sample size increases. Now, the only thing me and you are missing, okay, is the shape. I've drawn pictures like it's normal because I'm cheating. I'm interested in the shape of the sampling distribution of X bar. That's what I'm interested in. What the hell does the shape look like? Now, if me and you are going to do anything with this sampling distribution, you should know at this moment that this thing better be normal, or at least approximately normal if we're going to do anything. So, here's the thing. If I've got my population distribution, where I'm looking at one at a time, right? Every individual's value, and suppose it's normal with a mean of mu and a standard deviation of sigma. And then I'm looking at your sampling distribution of X bar. And anytime somebody talks to you about the sampling distribution, I need to know that you had an SRS of size whatever it is. How large a sample did you take? It turns out it will be normal with the same mean, right? I had to use the notation for it. And then, in other words, my population distribution is sitting up here with my population, right? It's got a mean and it's got a standard deviation. All of a sudden, I start taking samples of a particular size, and now I'm down here to where I'm looking at my samples, right? If the population distribution is normal, and I'm choosing samples of whatever size, let's say it's size 50, right? So now I'm looking at the sampling distribution of X bar, where I'm looking at N being 50. Surely, just drawing a sample and taking an average, if you're normal, surely I won't screw that up. And I don't. Normal population distribution, normal sampling distribution. All right. One last thought. What happens if the population distribution, one at a time, and I'm sorry, I'm going to say that to you every time tonight when I think about the population distribution, I'm looking at one at a time. In other words, I'm looking at every individual by themselves, because that's the way I think about it. What happens if the population distribution is hell, maybe it's skewed to the right, maybe it's skewed to the left. What can I say about the sampling distribution of our statistic then? Well, here's what I need. There's something called the central limit theorem. On page 361. What it's going to tell me about is the shape of your sampling distribution when your population distribution is not normal. So I got to write this down because this right here goes right hand in hand with the law of large numbers that I keep preaching about at the beginning of the class. It says this. Draw an SRS of size n from any population, I don't care what the population distribution looks like, with mean mu and finite standard deviation sigma. Notice in that line right there I have no mention of what the shape of that population distribution looks like. Okay? The punchline is this. When n is large. Okay, before I go any further. The more non-normal your population distribution is, the more skewed to the right or skewed to the left it is, the larger your sample needs to be. All right? the sampling distribution of the sample mean, get all the words in this one, is approximately normal. With me and you, this is the best we can do. And so what does approximately normal mean to me and you? Is normal. That's what it means to me and you. It doesn't matter what the population distribution looks like. When our sample size is large enough, then the thing we want to work with, the sampling distribution of X bar, is going to be approximately normal with the appropriate mean and standard deviation that I've been writing down like 4 or 5 times. Okay, so it doesn't matter what it looks like. What I'm telling you is, the more non-normal it is, the population distribution, the larger your sample needs to be. Can we all come to some agreement at this moment? Yeah, I know. All our eyes are rolling in the back of our head, and we even got to the point where your eyes should roll in the back of your head yet. Can we come to an agreement? Whatever problem somebody gives me, right? And whatever the hell they tell me about the population distribution, if they tell me it's normal, I don't have to worry about this. The sampling distribution is normal will continue. But let's say they don't even say anything about the population distribution being normal. And all of a sudden they're saying, okay, let's start taking a sample of size 10. 10 will be large enough so that this is true. I'm not going to argue about do I need to be 10 or 20 or 50. All I want you to know is the more non-normal it is, the larger my sample size needs to be. But whatever the problem tells me to use for the sample size, I'm going to be a happy camper and go on about my business. Right? I'm not going to think, okay, how normal is it? No, I don't give a shit. It's approximately normal. I'm going to do what I need to do at that point. All right? So, the bottom line is this. Me and you have a new normal distribution. It's called the sampling distribution of X bar. What does it tell me? It tells me what values X bar can take from all samples of the same size from the same population. The sampling distribution of X bar describes the behavior of X bar from one sample to the next. I got to remind you something that I started this chapter with. X bar is a random variable. Which means, just to remind you what this means, it means it is a numerical outcome from a random phenomenon. Well, what that means to us is, this idea of choosing a simple random sample of whatever size you want, and then calculating X bar, you're going to get a number, right? The simple random sample is the random phenomenon. I'm going to take you all the way back to the beginning of probability, and when something shows this random behavior, this chance behavior, what that means is it's unpredictable at any sample in this case. You choose any sample of, let's say, size 50, and you calculate X bar. Can anybody tell me what that X bar is going to be before we calculate it? And the answer is, hell no. Right? So X bar is unpredictable at any sample, at any trial, at any time you do it. But if it's showing chance random behavior, if it's coming from a random phenomenon, it's supposed to show some pattern if we do it over and over again. Does anybody know what the pattern is it's showing? That's the pattern it settles down to. It settles down to that sampling distribution of X bar that's described by a density curve that we know is going to be normal, we know where it's centered, and we know its standard deviation. This answers the question about, okay, You told me that X bar was a random variable. Yeah, I can buy that shit about it's unpredictable anytime you take a sample to calculate X bar, because that's just like flipping a coin, right? So what's the regular distribution of values does it settle down to? It's what the hell I got circled there in blue. It's the sampling distribution of X bar. Now, if we have a new normal distribution, what do me and you always do with a normal distribution? What are we always interested in? I'm always interested in area under the curve, chapter 3. Well, I would like to come over here, and I want to look at a homework problem because there's two parts to it, and that's the reason I want to look at it. I'd like to look at 1528 on page 372, and this is a typical kind of problem about this sampling distribution of X bar. And it's got actually two pieces in it, which makes it nice. So I'm going to go to page 372. And I want to look at problem 15.28. I'm going to go slow to get you started here, but it's going to look familiar to you. 15.28, Sheila's doctor is concerned that she may suffer from gestational diabetes, high blood glucose levels during pregnancy. There is variation both in the actual glucose level and in the blood test that measures the level. In a test to screen for gestational diabetes, a patient is classified as needing further testing for gestational diabetes. The glucose level is above 130 milligrams per deciliter, 1 hour after having a sugary drink. So in other words, you're at risk when your blood glucose level is above 130. All right? It says, Sheila's measured glucose level 1 hour after the sugary drink varies according to a normal distribution with mean 122 and standard deviation 12. So we have a normal distribution, got a mean of 122 and a standard deviation of... Now you notice how I used mu and sigma here. What we're looking at is all the measurements we would ever do on Sheila this way. In other words, what we're looking at here is this is your population distribution. That's the distribution of values taken. It's the distribution of blood glucose levels for Sheila in all possible tests we would ever do on her. That's your population distribution. So then we get to the question, and the question in part A is, if a single glucose measurement is made, what is the probability that Sheila is diagnosed as needing further testing for gestational diabetes? I want to know the probability that her blood glucose level, one measurement, population distribution, no averages, that X is greater than 130. This is dealing with the population distribution. This is where you're dealing at one measurement, one at a time. How do me and you handle this problem? Well, now, you guys can all look at me however you want about how do I handle this problem, but you just turned homework into me. And it seems to me like you did one of these problems where there was a normal curve involved. It might have been a multiple choice question. Something about maybe... I can't remember which one it was. I know I picked one of them, and I think it was multiple choice, right? It's the same question. I mean, I know I talked all kinds of crazy shit about some sampling distribution, but this is a problem that could have been from a previous chapter, right? They don't have to be here. How do I handle this? Well, I'm going to be crazy and start drawing you pictures. There's that normal distribution. It is centered at 122, and I'm going to label this for you as your population distribution. We are interested in 130. I want the probability that one glucose test is going to have her as being needing further testing to be greater than 130. How do me and you find that area that I got shaded in blue? Anybody remember z-scores? So here, your z-score formula is, you always take a value of the variable, you subtract off your mean, and you divide by your standard deviation. In this case, you're going to take 130 minus 122 all over 12. Somebody check me on the calculator, please. So my z-score here is 0.67. Now, you know I got to draw you the next picture, right? Because I always do. I'm always going to draw you the... Anybody know what that normal distribution is? That is your standard normal one, right? It's centered at 0 with a standard deviation of 1. Here I got 0.67, and I want the area to the right. So what do me and you do? We go to table A. We're going to the row that is 0.6. The column is 0.07. We're going to look that up and we're going to find area. There's my table A. I want to go to the 0.6 row, and then I got to go to 0.07, which is 3 from the right. So I'm going to read 0.06. Looks to me like I'm getting 0.7486. Please remember, the table always tells you to the left. That's point. Oh, I can't remember that. What did I say was 0.7486? 0.7486. That is 0.7486. I want to the right. How do I handle that? I take 1 minus what is to the left. So I get 0.2514 to the right. If that area is 0.2514 there, this area here is 0.2514. That probability is, so the probability that the blood glucose level of Sheila comes back greater than 130, meaning she needs further testing for gestational diabetes, based off of one test, has a probability of 0.2514. I could have gave you this problem here for homework for out of chapter 11. Right? I mean, hell, there was no averages there. That's just a straight up problem we did before. And then we get to part B. And part B says, now I'm going to be a little bit crazy with you. I can convince you that that was one at a time and that's just what me and you always do. But when I get to part B, it says if measurements are made on 4 separate days and the mean result. Hell, I'm reading the word. Mean result. You see that right there? You better tell me how many you took an average over. I need to know what is n equal to. How many did you take an average over? What was your sample size? Well, my sample size here is 4, right? Because we're going to average those 4 together. Now what it wants to know is, what is the probability Sheila is diagnosed as needing further testing for gestational diabetes when you're looking at the average over 4 days? So I want to know, what's the probability? You notice I'm not using an X there because I'm not looking at 1 at a time. I'm looking at 4 at a time and taking the average. The X bar is greater than 130. So the population distribution is normal. So I know the sampling distribution is normal. Don't need the central limit theorem. It wouldn't help anyway with n being 4. So I'm going to draw you this picture. I'm going to label it for you. This is your sampling distribution of X bar, where n is equal to 4. I know it's normal. It's centered at 122. What's the standard deviation? How do you find its standard deviation? It's supposed to be sigma divided by the square root of n. It's supposed to be the standard deviation of your population distribution divided by the square root of your sample size. So that means it's normal. Its mean is 122. What the square root of 4 is 2. That must be 6. Are we okay? The only difference between part A and part B, oh, I wrote a little X bar there. Shit, nobody's going to know whether you wrote that or not. It's right here. Standard deviation changes. The mean doesn't change. And so I know this guy is centered at 122, and I'm interested in 130, and I want the area to the right. All right. How do we always do these? We calculate a z-score. Now I'm going to do it like this time. I'm not going to write the formula out until we're done. I'm going to take 130 minus 122. Does everybody understand why I'm using 6? Because the standard deviation is 6. Here I'm going to get 8 over 6, which is 1.33. Anybody know how this problem continues now? That's still a z-score, right? So we're still going to deal with the standard normal. It's centered at 0, and I just got a z-score of 1.33, and I want to the right. What do? Same thing we always do. We run it for table A. I want to go to the row that's 1.3. The column that is 0.03. Right? Same as before. When I come over here and read 1.3, 0.03, what is that? The first column is 0, so I need to be the fourth one over. 1.3, fourth one over. It looks to me like I'm getting 0.9082. That's to the left. That gives me 0.9082. That's 0.9082. 1 minus 0.9082. What is this? 0.0918. If that area is 0.0918, then I'm hoping you understand that that one is 0.0918. So this probability is 0.0918. Now, I know it's about time to go home, but I want to compare the two problems. When I looked at one at a time, I got a probability of 0.25 something, right? When I took the average over 4 to see if I was greater than 130, I got a probability of 0.0918. Which one's more likely to happen? Is she more likely to need further testing with looking at 1 at a time or looking at 4 at a time? Which one has a higher probability? 1 at a time. That was almost 3 times as high. Right? Now, what's the only difference between part A and part B? That's what I got circled in front. You're looking at 4 at a time. Here, my standard deviation change. Now, I got to do one thing before we go. When we are dealing with the population distribution, sometimes I regret writing that n is equal to 1, but you're looking at 1 at a time. The z-score is that's the same one that me and you used in Chapter 3. That's the one we used in the probability questions in Chapter 11. The difference is when we're working with the sampling distribution of x bar, as soon as you hear those words out of my mouth, you've got to ask me too, okay, you had an SRS of size n, bigger than 1. What's my z-score actually look like? What's the formula actually look like that I want to use? Well, you're not standardizing a value of the variable. You're standardizing an average over some sample, right? You're standardizing an x bar. You're still going to subtract off the mean because it's exactly the same as the population mean. How did I get that 6 last time? Right? That's how I did that. And that's what I did back there when I standardized. It's just I didn't write the formula down because I wanted to write it down for you here. This is, the top is 1 at a time versus n at a time. Folks, there's 4 things you've got to be able to do out of this chapter. You've got to be able to identify parameter versus statistic. That's where we started last Thursday, right? You got to know what the law of large numbers says. You got to know what the central limit theorem says, and then you got to be able to do a calculation like what I just did here in part A and in part B. That's the 4 things. Yeah, I know I've talked 1 class and a half about all that shit. Those are the 4 things you need to be able to do. Identify parameter versus statistic, know what the law of large numbers says, know what the central limit theorem says, and then be able to do one of these normal distribution calculations, whether we're looking at 1 at a time, or 4 at a time, or 22 at a time, or 72 at a time, whatever it is. Be careful going to the house. We will move on to the next chapter 16 on Thursday.